part is really a live demo. We are going to start from a piece of code I prepared that corresponds to the baseline translation of this task stencil. So this is the stencils we are looking at. You already did this exercise to compute the Laplacian. And then I added this statement here, computing a very simple interpolation, just to show you that you can really fuse unrelated computations together for performance. But really, this doesn't need to be, let's say, even in the same in the same file, in the same let's say units of this to be merged together. This shouldn't be up to the user. So in our picture, you can combine the compiler can combine unrelated computations that need to be done anyways together to gain performance, but still separating them in the DSL. This is up to the user how to organize them. So this will be the code that we are going to see translated, and are going to optimize the CUDA code. This is the CUDA code. Let's briefly look at it. So it's one kernel per statement as defined in the baseline. So I number it kernel 1, 2, 3, one for each statement, of course. Then I prepared some stubs here to complete, in which we do the fusions. For example, kernel 3 and 4, 5 and 6, so on. I should add here instead we have the code that it's run on the CPU, and this will be the driver code, if you want, that will launch the kernels. So in order you can launch them, and then we will also have to change this part when we fuse. Okay, just need to go to put a bookmark. Okay. Here we will register the times that we obtain, because we are for each optimization, of course, starting from the baseline, because we are going to compile and run this, as I mentioned before, on a compute node of TSA, which is a supercomputer at from the Swiss National Supercomputing Center, which we are collaborating with. So maybe to just give you an idea of what is behind all of this, well, of course, you have some, again, we can classify this as driver code. This will prepare all the input fields, do some verification, and take the timings and so on. The same as it was for the exercises. And here, for example, we are applying again the Atlas meshing library to generate the mesh, and also to generate the fields. We use it also to fill the input fields and so on. Then there are these scripts that I will use. One is to compile. Well, let's not go into detail, but you can compile with NVCC, the media compiler, the code that we will touch, and then compile the driver and link them together and so on. To run, we of course need something to run on a compute node of a supercomputer, so we will basically use this use Slurm to do that. If you already know it, otherwise it's not that important. Okay, so first thing I want to check that we can compile and run the baseline, so what we got so far. That is something that can already come out of Dawn. So this is unoptimized but valid CUDA code, and we can see what happens. I'm sorry if this takes some time, but it is what it is. Also, I decided to print some information that NVCC can give you because we want to monitor whether there are register spills. And these you can look at for each kernel. If you see a number, if you see something strange here that is not 0 bytes, this would be register spills. Then, okay, after compiling, this started the run, which correspond to setting up the grid, the fields. So this is all done on the CPU. Then we upload these fields to the GPU, run it once to verify the correctness, do 100 runs to take the average timing, and see if the standard deviation is low enough, of course, of this average. And we take this timing and we put it into the in this table here. So we start from 3 milliseconds, and let's see how we can improve. So 3 milliseconds is one run, all the 13, sorry, they're not 13, they are 8 kernels, and average time of running the 8 kernels. So let's start by doing the first merging. We will fuse kernel 3 and 4, so these two statements. Let's see maybe why you can fuse them. Well, they are on the on the same iteration space, so on edges, right? And as you can see here, for example, they write into the same temporary, but the second one also uses the temporary, but here, if you merge them together, you really don't spare memory accesses because you cannot still remove this temporary. This is used then on the last, sorry, on the on this statement below. So let's proceed and fuse them together. Okay, kernel 3, I will just copy the code that I see here. Very simple, I just copy paste that. So this is kernel 3 now. I will just put the piece of kernel 5 that I need. So this is, sorry, of kernel 4. This is kernel 4. We don't need to replicate all of this. This is computed the thread index, setting up the iteration through the k levels, doing this iteration. This is something we can share. So we just need the computation. I would put it at the end here afterwards. Maybe you can already see that here we don't need to explicitly access it like this because this temporary is accessed at the same location. We can just use a local variable. This is for visualization because, of course, the lower level compiler will just detect the same as we did visually and optimize it already through a register. But it can do it only because these are in the same kernel. So we are really helping the lower level compiler to do the optimizations. And we need to change the run function, of course. So remove the calls to kernel 3 and 4 and just have a call to kernel 3 and 4, which I already prepared before. Okay. So if we did any mistake in this, for the exercise, we have this verification procedure that will validate the results. Also, if we did any mistake in the code, we will have the compilers complaining. So let's see. So maybe it takes some time to do this because we are doing this on the CPU. And usually, if you setting up the grid, filling input fields, this is a setup phase that if you think about a model, you need to do once, and it's not really relevant for performance. Okay, this is the timing that we got. It's already averaged. Check that standard deviation is low enough. Maybe check that you don't have spills, register spilled. I already know that, but in general it should be checked. So we already have some improvement, 2.65 milliseconds instead of 3. So already by doing one fusion, it's already nicer. Okay. Next, I think is, sorry, a bit lost. 5 and 6, which is very similar to what we just did. It's the second term of the Nabla computation, Nabla 2 computation. And again, we cannot remove the temporary. So maybe for simplicity, I can just remove these kernels 3 and 4 that we joined before. I just take kernel 5 and paste it here. And then I just take the computation of kernel 6 and paste it here. Bring it to a nicer form with a local variable. And do some cleanup. So the run function we need to change. We don't want to call the 2 kernels, but we want to call the fused one. Oops, just this one. Okay. So we fused 5 and 6 together. So now we should have 6 kernels instead of 8, if I'm correct. Again, you should check if there are register spills. Okay, let's take this number, check that the standard deviation is low, and compare. So again, some improvements. We are diverging from these 3 milliseconds that we got at the beginning. We are going. We are improving performance, of course. So the next one is again fusing these 2 statements. Let's see in detail. would be this one and this one. So again, this you can see. So they write, one writes on nabla2 vec and the other on interpolation output. Just to give you an idea, here we are computing on edges because interpolation outputs and nabla2 vec are fields on edges, so we can fuse them. They are completely independent statements, and they don't have any data dependencies between each other. So if we gain something here is because of hiding memory latency and avoiding the synchronization between kernels, which is really unnecessary. So let's do that. 7 and 8. So here again, I'm taking the part that is computing something and not the what is above. This is computing a reduction, as you can see. So it looks like there's more statements because reduction involves also a loop and so on. I just put it here, the correct one, yes. So here it's just about copy pasting. They are completely unrelated. I don't need to do anything else. And I will go ahead and remove the call to 7 and 8 and substitute with the fused kernel call. Okay, let's see if we did any mistake. The verification should catch it. Okay, so this is number that we got, and well, there is maybe some improvement, but it's not that much. It's barely noticeable with respect to before. And sometimes it's just that maybe there was no latency to hide in this case by just doing this, and in general, you cannot expect that fusing two statements will give always um, much performance gain. And again, it's the trend that that matters for us. So I'd say let's proceed. Before we proceed, maybe I can um, show you, because maybe you want to try this at home. Afterwards, I will share some slides on how to reproduce this. Maybe we can try to see what happens if we put an incorrect computation. So when you do your experiments, you have these safeguards, and I will show you what an incorrect computation will trigger. So let's say we add arbitrarily a number here to our computation, and let's try again to compile and run. Okay, this is the error that we got. L1 norm to I, verification failed for interpolation. So here, of course, I change our interpolation output by 1, and of course, this triggered an assertion on the verification. So this is our safeguard. So now let's remove the mistake, of course, and let's proceed with the next optimization, which, if I'm correct, is fusing two kernels that we already fused together. So before we fused these two together and these two together, now we will fuse again the old block. Now the question is there any temporary that we can remove? Well, actually not. Both temporaries that are written to here are used then in the next statement. Okay, so let's start from, for example, from the code of kernel 3 and 4 fused together, copy it. Five and 6. And okay, I leave some space here. Yes, I think I don't have to change anything here, just maybe yes, remove and call the fused kernel. Okay, let's try this. Okay, so let's retrieve the number again. And yeah, so now we got some noticeable improvement again. And yeah, I would say let's proceed. This will be the last fusing of dense loops. Sorry if this it's a bit repetitive, but really fusing dense loop is the one that gives the most of the performance. So this we can remove as we already fused that. So now we want to fuse this one. 3, 4, 5, 6. And we will have this stub field. Now we lack 7 and 8. Which is this one. So I'll just copy the computation here. Yeah. Okay. So maybe we can look at here. Now we are fusing these all blocks together. And you can see that since you have these two temporaries, these are only they only appear in this big block, and therefore we can get rid of them and use local variables instead. So I'm just going to do that, of course. So for example, here we already have this local variable that we used, but before we had to write into the temporary. Now we write again into the local variable. Same thing here. And here is the place in which we use those. So the 2D2 and so the term 2 minus the term 1. And of course, we need to adapt again the driver, remove these calls, just have the call to kernel 3, 4, 5, 6, and 7, 8. Okay. So again, the GPU on which we are running this experiment is a V100 accelerator. Okay. So this is the timing that we got. Let's compare it to the rest, and we can see here a lot of improvement. And since this was the first time that we removed some memory accesses, you can really see that memory was the bottleneck here. So the bandwidth was the bottleneck, and we reduced a lot this bottleneck probably, and we got really good numbers. So now we are almost at the runtime of the baseline naive translation. So if we go back to the code, das code, we have this block all together. Then these two are separate kernels, of course. But let's still look at this block, and we can notice that, for example, here you have an edge cell reduction, and also below you have an edge cell reduction. They are completely unrelated completely unrelated statements. So there is an opportunity to fuse. Just we should make sure that this statement is executed below this statement, of course. So what we could do is bring this reduction, the for loop implementing this reduction within the first one. Okay, let's try to do that. So this is our kernel. Now we'll have to try to find, so this is the last reduction. Okay, so what I will do first is just bring this code up to the point where we want to fuse. Okay, this should be the point. Maybe paste it above here and comment it out. Okay, so so to fuse them together, we just need to place the statements in the right place. Here, as I mentioned before, we don't need to replicate the access to the EC table. We just need to copy the computation that was done inside the loop and uncomment it, of course. And we need the last statement as well. Okay, so we are now computing two reduction with the same for loop. We don't need to change the kernel call. This will be the same call as we didn't fuse any kernel. We just need to try see what happens. Okay, we got this number. So let's see. Yeah, we can notice some improvements. Not that big again, but if you do more, you have more reductions that you can fuse. You can think of improving more. Let's do the last optimization. This is going to be very quick because I already prepared. This already comes from some DON generated code. Here we just have a define which says how many k levels per thread we want to compute, and to parallelize we just put it to 1. So before, one thread was computing for 80 vertical levels. Now we spawn more threads, of course, and each thread will compute for each location for 1k level. And this is sufficient to just go ahead and compile and run. Okay, this number that we got. And let's maybe have a brief overview. Well, what happened parallelizing over the K, as we mentioned, gives a really nice boost in performance. Overall, we went from basically 3 milliseconds to almost 1 millisecond. So really 1/3 on this simple example, though. And well, maybe I can. So as this workshop is really about DSL and the compiler, let's use actually what we presented and see what we get. So I think we don't need that. Okay. So I will use the tools as presented I think 2 days ago. So you can use Dask front to translate this Dask script here and pipe its result, which is SIR, into down opt. So at first we will do the baseline translation. So no option to down opt, no optimizations applied. Then we will use down code gen. with backend CUDA ICO, of course. Output should be called, so we can basically reuse the same driver as exercise CUDA.co, so the file we have been manipulating. So maybe I can show you that now this is looks bad because it was generated by Dawn. It's not formatted, and it's not the code that we used before. But then the compiler run scripts will work the same way. So instead of us doing manually the optimization, this time it will be Dawn. But this will be the first, let's say here we're not passing the optimization option, just the baseline translation naive. So we should get something that is similar to this number. So maybe Dawn baseline is going to be similar to that, of course. Okay, well, slightly more optimized, but that's okay. Let's see what Dawn optimized will give. So I'll just change this command line to add these optimizations. I get some warning, but that's okay. These are disabled passes of the compiler. Again, verification goes on. Okay, let's check this number. So Dawn optimize gives quite already a nice result. We know that all these optimizations above were applied except for this one, which is currently not supported. But this gives already a nice improvement with respect to the baseline. So I think here we can conclude the demonstration, and maybe I should give you pointer to how to replicate this. Let me just open this set of slides that then we will of course share. Okay, I hope you can see this. So this will be the same as the demonstration, but you can replicate at home. There are instructions, and of course, as I mentioned, you need access to a machine with a CUDA-capable GPU, either virtual or physical. Some requirements like the CUDA toolkit, GCC8. To format your code, you can use Clang format, but that's not strictly necessary. You need Spack, which is the package manager we are using at ESiWACE to install software, solve dependencies automatically. This, for example, will install Atlas from ECMWF, which is one of the dependencies for the exercise. Of course, the setup phase can take a while because Spack will compile all the dependencies. And first of all, you need to install Spack on your own. This you can find documentation at the Spack homepage. Then you need to clone ESiWACE Spack deployment and set up Spack to basically understand the packages that we want that we let's say deploy at Matthew Swiss. You need to run this Spack compiler find to make it recognize GCC8. Then of course you need to download the exercise. Here is a branch of this Git repo. Here you will find all the files that I've shown you so far. And you have script to aid you in the setup. So just launching setup, make sure that you are installed Spack correctly. So maybe type in your shell Spack and see if Spack is actually run. Then after the setup phase, you should always, when you do the exercise, source this load environment.sh, which will build the environment in which you can compile and run. And to test if the setup is working okay, you should try to call the tools and see if there's any error. And these are the compile script. This is the compile script to call NVCC. Of course, you need NVCC installed with the CUDA toolkit. It comes with the CUDA toolkit and GCC8. And then to run, you get an executable code exercise which you can run like as we saw in the demo. So if you want to do the last part using Dawn to obtain optimized code, with this you get the baseline as I showed you before. It's the same, and with this command you get the most optimized that you can get from Dawn. So I hope you can have fun trying to optimize this if you have the possibility to have an access to a GPU. I think it's time for questions. I hope I'm not too much out of late on time.
No, I think we're actually really good time-wise. So thanks a lot for this nice demo, Giacomo. And yeah, I will put the slides into the Friday Google Drive before lunch. So in case you guys want to have a look at it. So now we have some time for questions. And I will just give everyone some time if they want to type out something or want to digest all the things we just heard. Very nice. I see people typing. And of course, I really would like to encourage everyone to take this opportunity in case there's something unclear or something you're wondering about. And also simple comments and suggestions or feedback are very, very welcome. So please don't be shy, and we have time to address these things now. So I think the first question is ready. I will just read out the question. Does Dawn Dusk support somehow loading data into shared memory for reuse?
Okay, at the moment for unstructured we don't, but we plan to, of course. So maybe one use case is when you are out of registers, you detect maybe that your registers might not be enough, and you rely on shared memory, or when you have threads within the same block accessing most likely the same neighbors, and there we could also use shared memory. But so far, no, we haven't considered. So.
Okay, and then the next question is from Daniel, and he is asking, is Dawn already able to deal with optimize MPI synchronization calls?
No, unfortunately, we are not there yet. These would be in the future possible. Of course, we plan to do that, but at the moment, yeah, we are far from that. We have, let's say, in the uh, parallel model mentioned before, we already considered this possibility so that you are not really stuck with representation that is far from supporting MPI synchronization, but so far we have been focusing only on one node, one GPU.
Okay, I think we give it just a little more time for questions. I think this is a good question about MPI. Maybe a comment from my side. I'm not sure. So, for example, OpenACC, whether it does kind of support synchronizing arrays across MPI ranks, or whether this is done manually. But what I'm wondering is, I guess this could be seen as an attractive feature of such a DSL solution, the way I understand it. So that basically a DSL solution would take care of MPI synchronization, so that a domain scientist doesn't have to worry about when to exchange halos and trying to find out when it's necessary and when maybe it's not necessary, things like that. Maybe if someone wants to, they feel free to leave a comment on Slack or in the Google Doc or in chat. But yeah, interesting question.